I think now it's time to introduce our two speakers, or actually, I will only introduce our moderator today. I'm very happy to have Elliot Dalton with us. He is working for R&D Pharmaceuticals here at Bayer, and yeah, he's a lab head. And actually, Erin and Elliot met at the Science Awards ceremony this year and were co-hosting a very interesting and insightful session. And yeah, I'm handing over to you, Elliot, to start our session officially. Thank you.
So thank you very much, Tatiana, and yeah, it's an honor to be moderating the session, and Erin, great to see you again. So yeah, the star of the show, the recipient of your 2023 Early Excellence in Chemistry Award, live from Princeton, USA, Professor Erin Stache. Erin has had a remarkable academic career to date, with a CV that includes some of America's leading institutions and scientists. She studied for her undergraduate degree at the University of Wisconsin-Green Bay before earning her PhD on the topics of chemical and photocatalysis under Abigail Doyle and Tomislav Rovers. A bit of a switch, her postdoc in polymer chemistry under Brett Force took her to Cornell, where in 2020 she was promoted to assistant professor. Latterly, Erin's made the move to Princeton, where her group is now based. For me, a key component of Erin's success has been the way she's taken the scientific principles gained over her PhD and postdoc and then applied them to her lab's missions. The Stache lab develops novel polymerizations of biodegradable materials, identifies novel biorenewable polymers, and advances depolymerization strategies for commodity polymers. The group already has 15 articles in peer-reviewed journals, including JACS and Angewandte Chemie. Not only has Erin been recognized by the Bayer Foundation, but she's received awards including the National Science Foundation Career Award, the Department of Energy Early Career Award, and the ACS Petroleum Research Fund New Investigator Grant, reflecting the urgency and the high profile of Erin's topic and its potential to transform the sustainability of the chemical industry. Erin, the stage is yours. I am just so excited to see what you will show us today.
All right. Thank you, Elliot, so much for that incredibly kind introduction. And thank you again to Tatiana and the entire Bayer Foundation for selecting our research program for this award. It was an incredibly fun event to attend in February and receive the award and meet all of the great, fantastic scientists who are being recognized. And it's also amazing to see what the foundation is doing to try and advance science and equity, which is so incredibly important. But today I'm gonna steal the show a little bit and talk about our research and give you a little bit more detail than I was able to give in February. And so I'm going to focus on our polystyrene recycling strategies to generate commodity chemicals, as Elliot so nicely introduced in his introduction of me. And so you can see from this video that I have right here, we have a lot of plastic waste building up in our environment. And this is really because we have a linear plastics economy. We produce millions of metric tons of plastic every single year, but unfortunately the recycling cannot keep up with the existing plastic production. And so instead of having closed loop recycling where we can regenerate materials of high value, most of the material ends up in landfills or ends up in the environment and it's completely uncontrolled. And so this is a very societal problem, a very substantial problem that we are facing as chemists. And just to give you a sense of the scope, because 300 million metric tons of plastic is a little bit hard to think about in your mind, if we just think about water bottle production, so plastic water bottles that we frequently use in our daily lives, we produce about 1.3 billion bottles per year or per day. This is how much plastic this is compared to the Eiffel Tower. So that little mountain of plastic is nearly overtaking the Eiffel Tower. Now, if we consider how much plastic is produced in 10 years for the same type of water bottles, it's 4 trillion bottles. And this mountain is towering over the island of Manhattan. And so this is a lot of plastic, and this is just plastic water bottles. This isn't considering all the other plastic that we use, which is essentially in every element of our daily lives. You can't go 3 seconds without touching something plastic. I'm touching a ton of plastic right now, including my clothes. And so we produce a lot of plastic. The environmental impact is we're still trying to assess, but what's happening is that we're seeing plastic aggregate in the environment. We now have what's called trash island out in the Pacific Ocean, and more of these are forming. And it's estimated that in this trash island, in addition to other waste, there's about 1.8 trillion pieces of plastic. And this is just going to grow and continue to become a much bigger problem as time goes on, as we increase our plastic production. But recycling cannot keep up with the production, mostly because we don't have efficient recycling strategies. And so this is the challenge that I wanted to tackle as an assistant professor. How can we develop our own strategies in the lab to try and help remediate this plastic waste? And as Elliot mentioned, we do this from a number of different vantage points. We think about making or developing new polymerization strategies for making either degradable polymers, which if they get in the environment can break down into more benign materials, or will be inherently more recyclable if you can get them into a recycling facility. But really, we focus a lot on the plastic that we're already producing, the plastics that we make in millions of metric tons per year, because we're not going to be slowing down plastic production anytime soon. And so we think about selective upcycling methods for polymer waste to convert these into commodity chemicals. We can create economic incentive for recycling strategies. And then we also focus on what is the holy grail of plastics recycling, chemical recycling to monomer, where you can take the products or the trash and convert it back into the monomers, which can be afterwards polymerized again to make virgin materials, which are of equal or greater value than the product that you started with. And to do this chemical recycling, we really focus on photothermal conversion, and particularly using carbon black, as Tatiana mentioned in her introduction. And so first, just to give you a sense of what photothermal conversion is and the power that it obtains or has. So it's exactly what it sounds like, right? So photothermal conversion is converting photons into thermal energy. And so when you irradiate particles or dyes with visible light, it will convert those photons into heat, which will dissipate as it moves away from the particle surface. And so you end up getting these temperature gradients where you have very hot temperatures near the surface of the particle and more ambient temperatures as it moves away. Now, you could think of this as just fancy heating, right? You have a material that converts photons into heat, and then you can just heat up your reaction mixture and do that rather than using fossil fuels or electricity to heat a reaction. But it actually is a distinct heating mechanism in the most idealized form of photothermal conversion. So typically, if you think about bulk heating or pyrolysis, what happens is that you program in a single temperature, it reaches equilibrium, and then the reaction will proceed at a certain rate depending on the temperature. If you want to increase the rate of that reaction, all you can do is increase the temperature. But in doing so, you're also going to increase the rate of other reactions, other side reactions, which can complicate your product streams. But in photothermal conversion, because of the unique heating mechanism, you're only generating these thermal gradients near the surface of the particles. So instead of having this bulk solution all at one temperature, most of the solution will be at ambient temperature, and you'll have these localized hotspots where the particles are absorbing light and converting it into heat. So what that means is that most of the starting materials in the reaction mixture will not be doing anything, but the ones in proximity to the photothermal agent can undergo the reaction at a very fast rate because this temperature can be much higher than what you have in the bulk solution. And so when you have this idealized photothermal conversion system, you can promote very high activation barrier reactions with high selectivity due to these local thermal gradients. And so the way we first established this in my lab or demonstrated this concept was in a really valuable reaction, Newman quart rearrangement, where it converts phenols to thiophenols. And so essentially, this is an intramolecular nucleophilic aromatic substitution reaction to generate these thiocarbamates. When you give this enough energy, it can go through this Meisenheimer-like transition state where you build up negative charge, so very high activation barriers, and then converts the O to S transposition and forms this carbon-sulfur bond. And so this is a really useful reaction because you can think about all the phenols that we have in our commodity chemicals and pharmaceuticals and materials. And you can very simply convert these into thiophenols and get new chemical structures and new material properties. But there's no strategy to do this besides bulk pyrolysis, or no general strategy. Essentially, you need to overcome these activation barriers by heating these reactions to very high temperatures. And so we thought that we could use photothermal conversion to overcome these limitations. And we started by using carbon black. So carbon black, as Tatiana mentioned, is ubiquitous. You can find it everywhere. Most of the black materials out there are using some sort of carbon black pigment. And so what Megan did is she took carbon black, she mixed it with the substrate. So this is just solid mixing the two powders together, and then takes this vial and irradiates it with visible light, so just broad spectrum white light, for up to 40 minutes. Some of these reactions are done in less than 5 minutes, actually. And then simply by the end, she can just filter off the carbon black and get the product in up to quantitative yield. And so this works across the entire substitution pattern that has been explored for Newman quartz rearrangements. Even very high activation barriers proceed with really good yields and efficiencies. And we can actually tune some of the product distributions by changing the wavelength of light. So a very simple procedure, solid state chemistry, essentially mixing carbon black with a substrate, irradiation, and then you can filter off to get the product. So how does this apply to polymer chemistry and polymer recycling? So my group became very interested in polystyrene as a target polymer for developing new recycling methods. And one of the reasons is that polystyrene is a huge market. I'm sure you all know one of the most common sources or uses of polystyrene is polystyrene foam. It's nice. I'm here so I can actually bring in props to the talk. So polystyrene foam is one of the most common uses of polystyrene resin. This market is continuing to grow. It's used a lot in packaging materials, but the waste market is actually decreasing in value. And so it's very hard to get rid of polystyrene waste. Most of it gets landfilled because there are not good recycling strategies for polystyrene. Of the commodity polymers that we have, it's one of the worst for recycling. It also fills 1/3 of the world's landfills. Now, of course, this is by volume because most of polystyrene foam is air, but it still takes up a lot of space, and nobody wants more landfills showing up in their backyard. The recycling rate is very poor, but it's a great material. It's not like we want to get rid of polystyrene because it does its job. It's very inexpensive, easy to make. Industry has been making it for decades, and it's a great packaging material. It serves a purpose where most new materials cannot have the same efficacy. So we thought rather than banning polystyrene, can we develop recycling methods for this polymer so we can continue to use it and continue to keep costs low to the consumer? And so we questioned whether or not we could convert this polystyrene backbone into different commodity chemicals. You can essentially think about polystyrene waste as a resource for commodity chemical production. So if you could take this aromatic ring and convert it into other chemicals like acetophenone or benzoic acid, you can see these are much larger markets than the waste market of polystyrene. And of course, if you could do chemical recycling to monomer and generate styrene, you could repolymerize it. Or if you could generate things like benzene or phenol, you could really create a lot of economic incentive to develop recycling strategies to remediate polystyrene waste. The challenge is, of course, how do you convert polystyrene waste into these different commodity chemicals with selectivity? And so we became very interested in the environmental degradation of polystyrene. So when this material gets out into the environment, it will break down, albeit very slowly and over hundreds of years. But the mechanism by which it breaks down is photooxidative degradation. So essentially sunlight and the oxygen in the environment will react with the polystyrene backbone. It'll start to oxidatively cleave. You'll get all this oxidized polystyrene, and it'll break down into smaller and smaller fragments. Now, of course, this process is not very selective, and it's also incredibly slow. And so we want to increase the speed and the selectivity for the degradation. And so we were inspired by this work from Takaki, where they used iron trichloride, so a very cheap metal source, to abstract CH bonds from carbon backbones. And then in the presence of oxygen could generate these oxygenated small molecules. And so the way they proposed this worked is that iron trichloride will undergo photoexcitation, undergo a ligand to metal charge transfer, and generate chlorine radical. And as we all learn in sophomore organic, chlorine radical is a great hydrogen atom abstractor. Quickly abstracts even very strong carbon-hydrogen bonds. We proposed that this would abstract CH bonds from the backbone of polystyrene. We could generate free radicals, and then these would react with oxygen and start to break it down into these oxidized aromatic products. And then by getting selectivity over this HAT process, we might be able to divert the product streams. And so all of this work was carried out by one of my first graduate students, Seiwan. And what he first did is he synthesized some polystyrene in the lab, so standard radical polymerization, and then he subjected it to iron trichloride, oxygen, and broad spectrum white light. And what he found is that you could selectively break down polystyrene into benzoic acid. So about 30% of the polymer was converted into primarily benzoic acid. Small amount of benzaldehyde and benzoyl chloride, but these are very quickly converted into benzoic acid. A very small percentage of acetophenone, and the mass balance was just being oxidized styrene oligomers. He was able to further show that you could improve this process to get approximately 50 mol% of the polymer into benzoic acid. We also developed a degradation process in flow, so we could try and scale this up to multi-gram scale in a shortened time frame with the same sort of product selectivities. But very importantly, he tried or tested this chemistry on several different commercial polymers. So a lot of the research that we do in my lab is actually on post-consumer waste. Again, this is why I have a lot of polymer trash in my office and in my lab. It's all of our starting materials. We establish and develop our methods on post-consumer waste so that we can ensure that it is going to be compatible and effective on the waste streams that we are generating. And so what he found is that if you have a near pure polystyrene product like this clear lid, the process works with about the same efficiency. But as you start to move on to more complicated materials that are multi-material products, may have inorganic composites or other dyes, we do see a drop off in efficiency. And you can see with this black coffee cup lid, we see the efficiency drop off to almost no reaction. And so for one, this highlights the limitations of using photooxidative degradation to convert polystyrene into benzoic acid. But it also highlights the challenges that we face as chemists and why we need so many different, well, for one, why recycling is so challenging, because we have so many different products that could be based on a very simple resin. But the challenges that we face as chemists and engineers to try and develop unique recycling strategies for all of these different products. And we've done a lot more work in this space, developing more selective strategies, tuning the product distributions that we can favor acetophenone over benzoic acid. And as you can see, there's a lot of other people working in this space as well. But today I want to focus my talk really on our photothermal conversion work and depolymerization, which really was inspired by the fact that this black coffee cup lid did not work in the photooxidative degradation. So we didn't really observe any degradation, and we hypothesized this was because the black pigment was absorbing all of the photons, dissipating that energy as heat, and then not enabling any chlorine radical generation. And so this drove us to think about chemical recycling to monomer. One half of this equation is polymerization. We take monomers, we make polymers. We know how to do this. We've been doing this for 100 years. It's really the backside of this equation. How do we depolymerize? How do we break down these polymer chains into the monomers that they originated from? And the reason this is so challenging, for one, is that most of our commercial polymers are incredibly stable, right? We don't want our water bottles breaking down as we're trying to drink. We don't want our shampoo bottles to start disintegrating in the shower. We want these things to be stable for the lifetime of the product. As such, we tend to have very kinetically and thermodynamically inert materials. We also need to develop recycling strategies that are going to be compatible with the waste stream. So for one, multi-material products, and for two, if you've ever seen a recycling waste stream, it's not very clean, right? There can be a lot of different contaminants, food contaminants, and any particular application could contaminate the waste stream. We also need to achieve high monomer purity. So this is really important. You want to get a very clean product stream. Otherwise, you need to do additional separations at the end. And separations is a whole nother cost sink that commodity chemical industry deals with. And we want to get selectivity for a single monomer in a mixed polymer waste stream. We have sorting technology that has greatly improved. It's improving even further, but still, if we could find a way to get selectivity for a single polymer to depolymerize in a mixture of polymers, this would be a really amazing feat. And so we questioned, and other people have done this too, and this is a recycling strategy that is currently commercialized. Could we use bulk pyrolysis to activate these bonds and break down these polymers back into their constituent monomers? So the thermodynamics of polymerization or depolymerization, since it's just the reverse process, if we think about something like polystyrene, this polymerization occurs through enthalpic driving force, right? We go from a carbon double bond to forming a new carbon single bond. And so this polymerization is very enthalpically driven, thermodynamically downhill. Once you start this polymerization, it'll go all the way to the polymer and it will stay there. But there is a temperature dependence for polymerization. And at a certain point, the entropics of stringing all these monomers together is going to overcome the enthalpic driving force of the polymerization. This is known as TC, or the sealing temperature, in which the rates of polymerization and depolymerization are equal. They essentially reach an equilibrium. If you go above the sealing temperature, now you've actually destabilized the polymer enough that it wants to unzip back into the monomers. And so this is the regime where we really need to be if we want to induce depolymerization of commercial polymers or any polymers. We need to be well above the sealing temperature of the monomer so that we can push the depolymerization back to monomer. Now you can imagine for a lot of our commercial polymers, this temperature is very, very high. And so to reach these temperatures, there's a very high energy input. So for polystyrene in particular, first, if you want to break the carbon-carbon bonds in the backbone, you need to heat this polymer up to about 350 degrees C. That's to just homolize those carbon-carbon bonds, assuming you don't have any other unique functional group on the polymer, which for most commercial plastics, it will not have. Once you generate these radicals, then the sealing temperature for styrene monomer is greater than 400 degrees C. And so you really need to be above these temperatures in order to induce the depolymerization back to the styrene monomer. So very temperature intensive. Bulk pyrolysis is how polystyrene is currently recycled. There are definitely companies out there that perform bulk pyrolysis to generate styrene monomer. Typically, temperatures are about 500, greater than 500 degrees C, and you need to maintain these temperatures for the depropagation. Of course, this is very energy intensive, and so we question whether or not we could use photothermal conversion, use photons to drive these depolymerizations rather than electricity or fossil fuels. And so again, just to remind you of photothermal conversion and the distinct heating mechanism from bulk pyrolysis. With bulk pyrolysis, there's a single rate constant. So you need to heat this up to about 500, 550 degrees C in order to induce depolymerization. And of course, other things are going to be happening as well, and so you tend to get a lot of side reactions. But in photothermal heating, only the polymers that are in proximity to the carbon black will start to break down this polymer and start to unzip and generate monomer, which is going to be expelled from the surface of the carbon black, whereas the overall bulk temperature is much lower than the surface temperature of the carbon black. So you get a much faster rate of depolymerization and should get a much cleaner product distribution, as well as being able to use photons as opposed to standard electrical heating methods. And so where we started in this space, we were trying to identify carbon-based photothermal agents. And so Liat got all of this chemistry started. And what she did is she looked through the literature to find materials that had very low photoluminescence quantum yield. And so we hypothesized that if these materials aren't photoluminescent, then they're likely returning back down to the ground state in a non-radiative decay pathway, which means they're generating heat. So converting light into heat. And so what we did is we looked for the worst carbon quantum dots that we could find. So these are just colloidal carbon. We heat up ascorbic acid in water, and it generates some structure similar to this. And these were the worst materials, so they don't have any of the photonic properties that most people want carbon quantum dots for. But for us, this is a great opportunity because it's something very cheap, ascorbic acid or vitamin C. We can generate these materials, and then they'll generate these photothermal gradients so that we can hopefully induce depolymerization. And so we started with the model polymer. Liat mixed polyalpha-methylstyrene with the carbon quantum dots. She made a film. She irradiated it for 30 minutes and then generated the alpha-methylstyrene monomer in 85% yield, with the mass balance just being leftover alpha-methylstyrene oligomers. Now, notably, this reaction does not work with your standard photocatalysts. So these are very common photocatalysts that we use for electron transfer, energy transfer, to promote all these different types of reactions. Under our conditions, under radiation, these don't do anything because they photoluminesce. If they don't react with a polymer through an electron transfer, energy transfer pathway, they just generate photons and dissipate the energy in that way. So we don't see any reaction with a standard photoredox catalyst. Now, notably, this depolymerization strategy works across an entire breadth of polymer classes. It's not restricted to just vinyl monomers. It can work for anything that will thermally depolymerize because it's just generating heat. And so polyaldehyde, which were initially used as photoresists, depolymerize very easily under our reaction conditions, get high monomer yields. Alpha-methylstyrene, commercial polymers, polymethyl methacrylate or plexiglass, which you're all probably very familiar with, depolymerizes very well to generate methyl methacrylate monomer. And then very excitingly, an increasingly used biorenewable polymer, polylactic acid, depolymerizes with very high efficiency back to L-lactide monomer in 95% yield. Now, this is very important for one, that we're getting L-lactide monomer and not seeing any racemization of those stereocenters. So you need the L-lactide in order to get the properties of the PLA. And also, polylactic acid is best recycled through chemical recycling to monomer. It actually doesn't break down in the environment very quickly. It can be recycled under certain conditions in a recycling center, but chemical recycling to monomer is really the most efficient pathway for this polymer. So this worked, and it worked with an exogenous catalyst as well. We're using two different forms of photothermal catalysis in this case. And then, of course, polystyrene, the polymer that we're really trying to depolymerize. We took commercial polystyrene foam, added barium oxide, and induced depolymerization to about 43% yield using these carbon quantum dots. We were able to scale this up to 1 gram. We just made a powder mixture of the carbon quantum dots and polyalpha-methylstyrene. And then you can see the solid here, and then at the end, all this liquid is the monomer that was generated. But what you'll also notice is that these beautiful orange carbon quantum dots are no longer there. Instead, we've generated this dark brown mixture. And so what we found out was happening is that the dark brown mixture was still photothermally active. What the carbon quantum dots were converted into was still photothermally active, but they were further carbonizing over time, so they weren't thermally stable. As you can see here from XPS analysis, we see that the carbon oxygen content is decreasing, and it's basically turning into something like carbon black. Undeterred, we tried this in a number of different commercial samples. So again, the clear lid, clear cup, styrofoam cup, and then the coffee cup lid. And in all cases, we could mix the carbon quantum dots with the polymer in solution, remove the solution, irradiate, and generate styrene monomer. Very excitingly, we're able to do this in a solvent-free processing method. So we could take solid carbon quantum dots with post-consumer waste, so PLA, mix them together through thermoforming, so just hot pressing them together into a film, and then we could irradiate this without any real loss of efficiency. We can actually lower the catalyst loading as well to get L-lactide monomer back. So this was a great proof of concept. We identified a new photothermal agent that people hadn't been looking at before. We could depolymerize commercial polymers, including polystyrene. We had a few limitations here that we wanted to address. And so one was incorporating the photothermal agent into the post-consumer plastic, right? This is an extra processing step, which is going to increase the cost of recycling and hinder it being actually implemented on scale. And the second is that the photothermal agent was further carbonizing to something like carbon black. And so it wasn't stable, we wouldn't be able to reuse it, and people generally don't like materials to degrade or turn into something else as you're using them. You want to have thermally stable materials. And so with this information, we questioned, okay, if it's turning into carbon black, can we just use carbon black to depolymerize polystyrene? As Tatiana mentioned, carbon black is used extensively in many industries, but particularly in the plastics industry. So it's used very heavily in polystyrene plastics. You can see here just 3 that we found. We measured the carbon black loading or the black pigment loading anywhere from 3 to 5 weight %. Basically, any of the black plastic you see out there probably has some form of carbon black in it. It's used in up to 40 weight % across different materials. Black plastic recycling rate is nearly 0. Granted, most recycling is near 0, so maybe that's not too surprising. But black plastics in particular have not been explored for recycling. And so we questioned, okay, so we have these black materials, can we use the carbon black that is found in them to depolymerize polystyrene? So all of this work was carried out by Seiwan and Hanning, and Liat started all of this work. And so the first thing we did is we made pure, pristine polystyrene carbon black composites. So we took styrene monomer, we took carbon black, we polymerized them together and made a carbon black solid composite. Then we exposed this to visible light irradiation, and particularly using vacuum distillation to recover the styrene monomer. And what we found is that without any carbon black, the polymer is completely inert to visible light irradiation. It doesn't do anything, it doesn't degrade, it will absorb the light and just dissipate it as heat, but not enough to actually generate depolymerization. As we start to increase the carbon black loading, so even at 1 weight %, we start to see styrene monomer generation, so about 30 or 40%. And then around 5 to 6 weight % of carbon black loading is where we saw most efficient depolymerization to styrene monomer. So about 60% yield of styrene monomer, some dimer and trimer, which are the most common byproducts from depolymerization or polystyrene pyrolysis, and then a little bit of leftover polystyrene. So we're very excited that we could take carbon black, use it as a photothermal agent to depolymerize these lab synthesized polystyrene composites. This is our reaction setup. You can see here, we're irradiating the vial. It goes through a distillation setup so that we can recover pure styrene monomer in the receiving flask. You can see up here in this proton NMR, this is pure styrene monomer. All those peaks belong to styrene. In the reaction vial, we have leftover polystyrene with a little bit of trimer. And then in the condenser, we have the dimer. These are just separated based on boiling point. But a video is worth a lot more than anything I could say. And so this is the a sped up image or a sped up video of our depolymerization process. So you can see as soon as we turn on the light, it starts generating those thermal gradients, starts homolyzing those carbon-carbon bonds and depropagating to styrene monomer. So you saw some bubbling down here. That's the styrene monomer escaping the system. And you can see it's collecting up on the vial and being pulled into the vacuum distillation. And what's left over is some of the trimer, as well as leftover styrene oligomers and carbon black. But it's incredibly fast. I mean, this video is very fast, but it takes about 20 or 30 minutes to depolymerize this mixture. And the reason we think this works, you might think, okay, if the bulk temperature is lower, why don't we see repolymerization of the styrene into polystyrene? And we think it's because the polymer is in close proximity to the carbon black. They're both in solid phase. The carbon black heats up, it starts to break down the polymer, generates styrene monomer, but it's so hot near the surface of the carbon black that the styrene monomer is quickly expelled away from the reactive functional groups on the polymer. And so that's why we don't see repolymerization, even though the bulk temperature is much cooler than near the surface of the carbon black. We tried this out in some commercial polymers just by mixing carbon black with white polystyrene, so just melt processing these together. And what we wanted to do in this case was see what would be the effect of different contaminants on the depolymerization. We hypothesized that because this is just a purely thermal process and we're not doing any other special catalysis, impurities wouldn't really affect the depolymerization. And so we looked at different food contaminants, canola oil, soy sauce, orange juice, and sugar or sucrose. We mixed these in at 20 weight% with the polymer mixture. So it's a pretty high contaminant loading. And what we found is that in all cases, we see almost comparable depolymerization efficiency to the standard reaction conditions. We do see a little bit of loss of efficiency with ascorbic acid, but this is a known radical scavenger, and so that kind of makes sense. But because it is a purely thermal process, these different additives are not interfering with catalysis here. And then, of course, does this work on existing commercial waste? Like I said, carbon black is used extensively in the plastics industry, up to 40 weight%. These were just 8 different polystyrene containing samples that we collected. We know they're polystyrene because you can see here, there's this little number 6 polystyrene resin identification code. All that tells us is that it has polystyrene resin. It doesn't tell us how much. It doesn't tell us the carbon black loading. It doesn't tell us what plasticizers or surfactants or other inorganic additives or other copolymers might be in there. But we know that it has polystyrene resin. And you can see here, I'll just point out the sushi box because we know that this has about 70% polystyrene, and then the other 30% is polyolefin. Inexplicably, not entirely sure why, but this one in particular has only about 70% styrene or polystyrene. But again, in all cases, these are all black plastics. They all contain polystyrene, and we didn't do anything to these. All we did was cut them up to put them in a vial so we could irradiate them with visible light. No other carbon black was added. No other catalysts were added. It's just the plastic that the plastic manufacturers produced, got used, and then we found and put into our system. And in all cases, we're able to generate styrene monomer from these existing black plastics. So the additives that plastics manufacturers are putting into these black plastics can induce their depolymerization with pretty high efficiencies. Now, we wanted to see if we could use essentially zero energy input or zero electricity input into these systems. Because with the LEDs, we're still plugging into the grid. And so what we did is we want to see if we could use sunlight, use focused sunlight in particular, to depolymerize these existing black plastics. And so what Hanning did is she took first pure polystyrene, focused the sunlight with a Fresnel lens or a magnifying glass, if that's what you have. And what she saw is that the polystyrene melted, but nothing else happened. It was completely intact. The solar radiation was not enough to depolymerize or photodegrade the material in the time frame that we looked at. However, when she took black polystyrene foam, so the sample that I had shown you on the previous slide, cut it up into small pieces, put it out and irradiated it with sunlight, what she found is 80% monomer generation. And this was in 5 minutes. So just 5 minutes of solar radiation, she could depolymerize the black polystyrene into 80% monomer. The mass balance was a small amount of dimer and trimer, as would be expected, but this type of styrene monomer yield is competitive or outcompetes existing pyrolysis technology. And again, this is just using the additive that the plastics manufacturers are already putting in the samples. But the really exciting thing was that all of this is based on black plastic, right? If we have clear white plastic, nothing happens. We questioned, because we're not consuming the carbon black, could we use the black plastic to first depolymerize that polystyrene and then essentially use it, I won't say as a catalyst, but use that carbon black to depolymerize white polystyrene in the same mixture. And so what Hanning did is she took different weight percents of black plastic with clear plastic, so from 0 to 100 weight percent, irradiated the mixture with white LEDs, and in all cases, she found depolymerization of both pieces of plastic. So it first depolymerizes the black plastic, and then that carbon black can be used to depolymerize the clear plastic. So this is using lab LEDs. If we move to sunlight, we can get near comparable efficiencies to our pure carbon black plastic, just using sunlight, and again, using as low as 10 weight% of the black plastic. And to demonstrate this point even further, she found a mixture of other polystyrene products, so yellow styrofoam, a red solo cup, this clear plastic cup, and I think this is 25 weight% of this black styrofoam. Same experiment, mixes it all together. You can see here what the mixture looks like, irradiates it with LEDs. Again, we're seeing about 45–50% yields. And with sunlight, we're seeing, again, near comparable depolymerization efficiencies. So the entire mixture is being depolymerized, not just the black plastic, showing that we can use the black plastic to depolymerize that, as well as other plastics in the mixture. And of course, another video just to show how quick and easy this process is. This is using sunlight. So we don't show the focusing lens here, but you can see what's happening in the vial. As soon as she starts shining light on this or focuses the sunlight, it instantly starts depolymerizing. And this shows that you can do this under static vacuum as well. So it doesn't need to be under active vacuum distillation. And so with that, I just need to thank all the people who did the work, because I did nothing, and I have a great group of students that I get to work with. I tried to highlight them as we went through. So Seiwan, Megan did some of the Newman Court work, and then Hanning and Clotilda have done a lot of the depolarization work, and of course, Liat started everything. Thank you to all the funding agencies for supporting this work. Thank you to the Bayer Foundation for recognizing our research with the 2023 Chemistry Award. Thank you again so much for hosting this event and letting me talk about this in a little bit more detail. I'd be happy to take any questions.